Hello my dear students, welcome to the next lecture in analog electronics. In this lecture we are going to discuss the conversion efficiency of class B power amplifier and also distortion in amplifiers. So as we have already mentioned, in class B operation the transistor stays in the active region only for half the cycle. The Q point is fixed at the cutoff point of the characteristics and the power drawn from the DC supply by the circuit under quiescent conditions is small. We know that the output current flows only for 180 degrees. Okay. Now this shows the waveforms representing class B operation. As you can see, only the Q point is at the cutoff and half of the waveform is reproduced. Okay, so the half of the signal is reproduced, which means there is sufficient distortion if the transistor is simply operated at this particular operating point. Now this is once again showing the waveform. This IC max is the maximum value of collector current. Now this is the AC load line and Q point is here, and VCE is the maximum. This is the maximum swing of VCE. Now let us calculate the power and efficiency. For a simple class B amplifier, input power is again VCC into IDC. What is IDC? IDC is the average or direct current taken from the collector supply. If IC max is the maximum or peak value of the collector or output current, then what is IDC? It is a half wave rectified waveform. Therefore, you will get it as IC max by pi. Okay. Now, what is the input power? Substituting for IDC, it is VCC, IC max by pi. This is just integrating from 0 to IC max sine theta from 0 to pi, okay, over the entire cycle, that is 1 by 2 pi. Now what is RMS value of collector current? IC max by root 2. RMS value of output voltage VRMS is VCC by root 2. If we know this, what is the output power during the half cycle? P out AC, it will be half IC max by root 2 into VCC by root 2. Why this half? Because power is developed during one half cycle only. So DC power loss in the load resistance, that is RC, if we are considering RC or RL as the load, this IDC square RC or IDC square RL will be the power that is lost in the load. So on substitution you get IC max by pi whole square into RC. So DC power loss in collector region or transistor will be P in minus this loss in R load resistance and minus the output AC power, that is the power that is lost in the transistor region. Okay. Overall efficiency will be given by P out AC by P in AC, or it is nothing but IC VCC by 4 as we have got here, divided by IC max into VCC by pi, and you will get the maximum efficiency in class B operation as 78.5%, which is higher than class A operation. Now the conclusion about simple class B power amplifier is that severe distortion occurs because of total absence of negative half cycle from the output, as average current in class B operation is IC max by pi is less than that in class A operation, so power dissipation is less and overall efficiency is high, that we got it as 78.5%. Okay, now in general there is an overall efficiency expression in general which is given by, there is no derivation for this. For the time being, it is 78.5 into 1 minus VCE min by VCC, that is overall efficiency. Now zero signal input represents the best condition for class B operation as collector current is 0. This is quite contrary to class A operation. In class B operation, the transistor dissipation increases with increased input signals, and half sine wave type of collector current contains very pronounced even harmonics. We will see harmonics, particularly the second one. Such impulses can be made useful either by using push-pull arrangement or by employing tune amplifier. We will discuss push-pull arrangement. Okay. Now this is a simple problem you can go through. For a class B power amplifier providing 20 volt peak signal to 16 ohm load, that is a speaker, and a power supply of VCC equal to 30. And this much data is given. You are asked to determine the input power, output power and circuit efficiency. So maximum value of output signal is given as 20 volt, that is VCE max is given as 20 volt. Okay. Now maximum peak value of collector current will be, IC max will be VCE max by RL, that is 20 by 16 will give you 1.25 ampere. Input power expression, you know, this is the output power expression, and you can find out the input power and output power. Circuit efficiency, obviously you will get it as 78.5%. Next we'll see class B push-pull amplifier. Why do we need this push-pull amplifier? Because the previous one we saw that only half cycle is being reproduced because it is in the cutoff. In this we are making use of two such transistors which are connected complementary, and then we are reproducing this half cycle also. So the signal is reproduced. Not just the positive half cycle, but the negative half cycle also is also reproduced if we arrange the transistors like this in a push-pull arrangement. One is pushing the positive half cycle, this is pulling down the negative half cycle, and finally you are getting the full signal which is amplified. So for that, just go through this circuit arrangement. Here you can see two identical transistors are needed, that is Q1 and Q2. So these are connected to the base of these transistors are connected to the opposite ends of the secondary of the input transformer TR1. This is TR1. These are connected to the opposite ends. Okay. The load resistance RL is coupled to the collector terminals of the two transistors through output transformer, which is TR2. The emitter terminals of the transistors are connected to the center tap of the secondary of the input transformer TR1. You can see that this is connected to the center tap of TR1. Okay, while the supply VCC is connected to the center tap of this TR2. So the number of turns here will be equal to the number of turns here. So this total number of turns will be 2N1 here. Okay. So we have got balanced circuits. So now here zero bias is required for operating point to be at cutoff. The two bases of the transistors are therefore grounded. Okay. Now let us see how the circuit operates. When this input signal is applied here, the center tap secondary of the input transformer is developing two signals which are identical but in phase opposition. You can see this is one signal, this is another signal. So this these are in phase opposition. So this transistor is going to conduct during this positive cycle only, isn't it? So the transistors Q1 and Q2 are driven by these signals. Now when V1 is going positive, V2 is going negative. This is V1, this is V2. When V1 goes positive, V2 is going negative. Okay. So the transistor Q2 is being biased off, and when transistor Q1 is biased on here. As the collector current in Q1 increases from 0, it produces half sine wave. Okay. Across the upper half of the primary of the transformer. So half is produced here. Then the other case, when this begins to go negative, what happens? This goes positive, then Q2 starts conducting, isn't it? So when Q1 is off and Q2 is on, half cycle of the voltage waveform is generated across the lower primary. So this is generated. You know this 180-degree phase shift will be there. So this will be generated on the secondary. Okay. So the effect of the two cycles in separate halves of the primary output transformers is to produce the magnetic flux in the core of this particular transformer TR2. So which is flowing in one direction and then in the opposite direction. So this flux is linking with the secondary of this particular transformer, and it generates the complete sine wave output which is passed to the load. Okay. So that two transistors are said to be operating in push-pull. That is why this is known as push-pull transformer. So you can see a full sine wave is obtained at the output using this class B operation, but we require two transistors. That is the only difference here, and the circuit arrangement has to be understood very well. Next we'll see the so this is just explaining the connections of the circuit. Then we'll see the conversion efficiency of class B push-pull amplifier. The input power P in DC is equal to again VCC IDC. But you see here IDC is the average of the current that is drawn from the collector supply. In this case, you are getting, in fact, the cycle is reproduced we mean in the negative half cycle as well. So it is like a full wave rectified current drawn from the DC source. So you will get the expression for IDC as 2 IC max by pi. The period is 1 by pi. Now P in DC will get this particular expression. Now AC power output. Again here it is VCC by root 2 into IC max by root 2. No, there is no half term. Power is obtained in both the half cycles. So it is VCC IC max by 2. The collector power dissipation for the two transistors together will be the difference of P in minus P out AC, and you will substitute the expressions here and you get 2 IC max VCC by pi minus VCC by 4, and the overall efficiency again you will get it as 78.5 because you have VCC IC max by 2 and 2 VCC IC max by pi. So you will get it as again 78.5% for class B push-pull amplifier. Now, after we have discussed about the power amplifiers class A and class B, their conversion efficiency, then let us see what is distortion in power amplifiers. The purpose of an amplifier is to boost up the voltage or power level of a signal without changing the wave shape of the signal. So if the wave shape of output is not exact replica of the wave shape of the input, we say that distortion has been introduced by the amplifier. An ideal amplifier will amplify a signal without changing its wave shape at all, and such an amplifier which faithfully amplifies a signal is known as high fidelity amplifier. So class A will try to reproduce the signal faithfully, but there may be distortion introduced due to several other reasons. So there are three types of distortion. These may exist either separately or simultaneously in an amplifier. They are frequency distortion, phase or time delay distortion, and harmonic, amplitude or non-linear distortion. Let's see what is frequency distortion first. In practical situations, the signal is not a simple sinusoidal voltage. Of course, you may not see a sound signal which is a simple sinusoidal voltage. It has a complex wave shape. Such a signal is equivalent to a signal obtained by adding a number of sinusoidal voltages of different frequencies. Hope you have an idea about Fourier analysis. So this is a signal will be a combination of sinusoidal signals of different frequencies which are added up. These sinusoidal voltages are called frequency components of the signal. If all the frequency components of the signal are not amplified equally well by the amplifier, then frequency distortion is said to occur. That is, there may be many frequency components which are added together to form the particular. Suppose this is a signal. It will be a suppose you have a signal which is a combination, different amplitude. So this will be a combination of different, one cycle if you take it will be a combination of different frequencies which are summed up to produce a particular signal. So this one cycle is formed by a combination of these. So if all the frequency components of this particular signal are not being amplified equally, then frequency distortion is said to occur. Phase distortion is said to occur if the phase relationship between various frequency components making up the signal waveform is not the same in the output as in the input. It means that the time of transmission or the delay introduced by the amplifier is different for various frequencies. The reactive components of the circuit are responsible for the phase distortion to happen. This distortion is not important in audio amplifiers. Our ears are not capable of distinguishing relative phases of different frequency components, but this distortion is objectionable in video amplifiers used in television. Next, we'll see what is harmonic distortion. This type of distortion is said to occur when the output contains new frequency components that are not present in the input signal. In frequency distortion, we saw different frequency components are present in the input signal, and if they are not faithfully reproduced in the output, then frequency distortion occurs. So that may be due to the, if you take the RC coupled amplifier, below the cutoff frequency the gain is decreasing, and above the upper cutoff frequency the gain is decreasing. In that case, such high frequency and low frequency components may be missing in the output. That is the case in frequency distortion. But here you see the output will contain new frequency components which are not present in the input signal. These new frequencies are the harmonics of the frequencies present in the input. What do you mean by harmonics? If you take an example, if the input signal consists of two frequency components, it's an example, it's just 400 Hz and 500 Hz. These are the frequency components in the input signal. If the amplifier gives rise to harmonic distortion, then output will contain this fundamental component, that is F1, which is a fundamental component. F2 is also the fundamental component. These two are already there in the input. Besides these two, there will be second harmonic of F1, second harmonic of F2, third harmonic of F2, third harmonic of F1, etc., etc., etc. What do you mean by that? Second harmonic means the multiple 2 into 400, 2 into 500, that is 800 Hertz. Then you have 1000 Hertz. Then you may have 3 times the fundamental frequency, that is 1200 Hertz, or 3 times the fundamental frequency 500 Hertz, which will give you 1500 Hertz. So these components are getting included in the output because of some circuit reasons. So that is known as harmonic distortion. So if you take the plot of the voltage magnitude to frequency, this is, you can see F1, F2 are the fundamental components in the input Vi, but the output may contain, apart from F1, F2, 2F1, 2F2, or 3F1, 3F2, like that. See that its magnitude is less than the fundamental. So harmonic distortion in an amplifier occurs because of the non-linearity in the dynamic transfer characteristic curve. What is the dynamic transfer characteristic of the plot between Vi and IC? Suppose it is non-linear. You see the input voltage is here. The output may not be exactly reproduced because of the non-linearity. Okay. So in power amplifiers, the input signal is large. The change in the output current is no longer proportional to the changes in input voltage. So if in the simple small signal amplifier, the operation of the amplifier is in the linear range of the characteristics, but in power amplifier of the characteristics of the transistor. But in power amplifiers, since signal is large, it may go to the non-linear region of the characteristic as well. So the transfer characteristic may become non-linear, and the output change with input is, when it is non-linear, there may be slight distortion in the AC signal which is being reproduced. If the input is a sinusoidal voltage, the output is no longer a pure sine wave. This type of distortion is also sometimes known as amplitude distortion or non-linear distortion, or it is harmonic distortion. Now this is an example showing the distortion due to harmonic components. So harmonic components, as I said, it is the multiple of the fundamental frequency. So fundamental frequency, suppose it is omega. So this is V1 sine omega t, which is the fundamental sinusoidal component. We are explaining with a sinusoid. Okay. Now, so this is the second harmonic component. What does it mean? This is minus V2 cos 2 omega t. Minus means it's the phase shifted by 180 degree, but at the same time it is cos 2 omega t. 2 omega t means twice the frequency of this fundamental. Now this is V3 sine 3 omega t. You can see its frequency is 3 times the fundamental frequency, which is 3 omega t. Suppose you add these three signals. So you can see it is added here. V1 sine omega t, this black one. Then it is added with minus V2 cos 2 omega t, and it is added with V3 sine 3 omega t. So these are the harmonics of this particular fundamental waveform. So when these three are added together, you get this blue waveform. See, this blue waveform is not a pure sinusoid. It is not in phase with V1 sine omega t. When you add these three waveforms, you get a waveform which is due to the fundamental second and third harmonics together, or it is a distorted waveform. So this is how the waveform is distorted because of these particular harmonic components. Or in the other way around, if you say, if you get a distorted waveform at the output of the amplifier because of the circuit reasons, that is operating, it may be because of the operating point, it may be because of the operation of the signal in the nonlinear region of the characteristic curve, or the characteristics of the transistor. Finally, if you get an output which is distorted, you can say that this is harmonically distorted. It is composed of the fundamental component of the signal as well as the harmonic components of the signal. These are summed together to produce this particular distorted wave. Now we can calculate the harmonic distortion. We can quantify this. A signal is considered to have harmonic distortion when there are harmonic frequency components, not just the fundamental component. If the fundamental frequency has an amplitude A1, amplitude, what is that? The amplitude of this particular fundamental signal. This is A1. Okay. The peak value of this sinusoid is A1. Okay. Now, and the nth frequencies, we are taking arbitrarily nth frequency component has an amplitude an. What is harmonic distortion? The percentage nth harmonic distortion is equal to magnitude of an by magnitude of a1 into 100. Now you can go through this example. Calculate the harmonic distortion components for an output signal having fundamental amplitude of 2.5 volt, second harmonic amplitude of 0.25 volt, and third harmonic of 0.1 and fourth harmonic amplitude of 0.05. So these three we can find out. So distortion due to second harmonic is A2 by A1 into 100. Due to third is A3 by A1 into 100. Due to the fourth one is A4 by A1 into 100. You will get that the second harmonic component is contributing to 10% distortion. Third harmonic component is contributing to 4%. And higher order harmonics, the percentage is less because the magnitude is less for higher order harmonics. Now, total harmonic distortion. When an output signal has a number of individual harmonic distortion, just as we saw, the first, second, third, like that, if there are many harmonic components, the signal is said to have total harmonic distortion based on the individual elements as combined by the relationship. What is that? Total percentage THD, that is total harmonic distortion percentage THD equal to the square root of D2 square plus D3 square plus D4 square plus etc. into 100. Okay. So calculate the THD for the amplitude components given in the previous example. We got D2, D3, D4 and all. So using the computed values of D2, D3 and D4, we can substitute. Here there are only three components, that is second harmonic, third harmonic and fourth harmonic. So you substitute here, you will get it as 10.95%, which is the THD introduced in the waveform because of the harmonic components. Now for the signal occurring in class AB or class B, the distortion may mainly be because of the even harmonics, of which the second harmonic component is the largest. So determining the second harmonic component is, we have a method to determine the second harmonic component. So for that we are considering a waveform. The variation of IC is observed here. So when you observe it now here, you may not see any distortion, but we are trying to find out an expression for the second harmonic component or the magnitude of the second harmonic component using this 3-point method on the collector current waveform. So here a collector current waveform is shown with quiescent minimum and maximum signal levels. Quiescent means this is the quiescent condition, ICQ. The operating point is fixed here. So this is the maximum value of IC, this is the minimum value of IC, this is the output current which is DC shifted. So we are defining an equation that approximately describes this. If the signal is distorted, we are describing it like this: IC equal to ICQ plus I0 plus I1 cos omega t. This is the fundamental component and this is the second harmonic. So I2 cos 2 omega t it is. Okay, I2 cos 2 omega t. Now, the current waveform therefore contains which all components? First one, ICQ. This is the which occurs with zero input signal. This is the quiescent component. That is the DC component. An additional DC current I0 due to non-zero average of the distorted signal. If the signal is distorted, suppose there is another additional DC component, let it be I0. The fundamental component of the distorted AC signal, fundamental is I1, and the second harmonic component is I2 at twice the fundamental frequency. This is cos 2 omega t. There is a correction. Although other harmonics are also present, only second is considered here because we are assuming the second harmonic component is dominant. Okay. The second harmonic component is also an even harmonic component. Okay. Now, we are going to equate to the points in the waveform. How? This is the point number 1. At point number 1, we say here we have taken this is omega t equal to 0. So in the equation for IC, if you substitute, IC is, what is IC? IC max at omega t equal to 0. So IC max is equal to ICQ, the the quiescent condition collector current plus I naught plus I1 cos 0 plus I2 cos 0. So simplifying this expression, you get IC max is equal to ICQ plus I naught plus I1 plus I2. At point 2, you can see the collector current is going to ICQ. Okay. So what this you can write it as IC equal to ICQ equal to ICQ plus I naught plus I1 cos pi by 2 plus I2 cos 2 pi by 2. Okay. So this is the cos 0 is substituted with pi by 2. Then there was 2 omega t here, isn't it? So 2 pi by 2. So you get an expression ICQ equal to ICQ plus I naught minus I2. Similarly at point 3, at this point IC is taking its minimum value, IC min ICQ plus I naught minus I1 plus I2. So you got these three expressions. From these three equations, if you solve simultaneously, it will give you these results. I naught will be equal to I2 equal to IC max plus IC minimum minus 2ICQ by 4, and I1 is equal to IC max minus IC minimum by 2. Now you suppose this waveform was a distortion-less waveform. Suppose this waveform which we discussed was distortion-free. You see here, this IC, if it was distortion-free, then IC max will be 2 times ICQ. We have already discussed. Or the DC component will be simply IC minimum by 4. Okay. So, and what about the fundamental component? It will be IC max minus IC minimum by 2. So, if distortion is there, then obviously I0 and I2 will have the values, not just I1. Otherwise, only I1 will take the value. So, if distortion is absent, then only the DC component, because of the what is that DC shift, that is ICQ will be present. Only ICQ will be present. Otherwise, IC max plus IC minimum, you can see from the waveform. IC max plus IC minimum, if you consider the full swing of the particular waveform, then it would have been IC max plus IC minimum would have been simply 2 ICQ. Okay. So, we are not going into such details. Now, for the time being, we have got the expression for the magnitude of I0, I2 and I1 here. So, we can express the definition of second harmonic distortion like this. What is D2 here? It will be this magnitude I2 by I1 into 100, and you can insert the values or expressions you have obtained for I2 in this particular expression. Okay. So, this is IC half IC max plus IC min minus ICQ by IC max minus IC min into 100. You have substituted these two expressions. Now, in a similar manner, for voltage also you can find out the expression for second harmonic distortion. Now, this is a particular problem where the values of VC min, VC max, VCQ are given. Use the above expressions and find out the harmonic distortion in these two particular cases. For these two particular cases, find out D2. You can go through this problem. Now, power of a signal having distortion. So, when distortion occurs, it is going to affect the output power, isn't it? So, the output power calculated for undistorted signal is no longer correct. For fundamental component, it will be I1 square RC by 2. Now, here you will see this I1 is the peak value. That is why this by 2 has come. It's not the RMS value. I1 is the peak value. The total power due to harmonic components will be the sum of these. I1 square RC by 2 plus I2 square RC by 2, like that it goes. So here if you substitute, then the total power can also be expressed in terms of total harmonic distortion. It will be P is equal to 1 plus D2 square plus D3 square plus etc. I1 square RC by 2, or the fundamental power into 1 plus THD square will give you the expression for the output power in case there is a distorted output wave. Now this example is giving you the output power because of the distortion D2, D3 and D4. So if you know D2, D3, D4, THD is root over D2 square plus D3 square plus D4 square, And the power equation for fundamental power will be I1 square RC by 2, and the total power you can calculate as 1 plus THD square into P1, and you will get it as 64.64 watt. Please note one thing here, the total power is due to mainly the fundamental component. Even with 10% second, we got 10% THD because of D2, but still it is very small, it is not affecting the fundamental power much. The next important point is crossover distortion. This crossover distortion comes into picture in our class B push-pull power amplifier. You know, in class B push-pull amplifier, the output is reproduced like this. One cycle is reproduced by Q1 transistor and the other second cycle is produced by the Q2 transistor. We have seen the waveform. But one point here is, for a transistor to be in the active region, the base emitter junction must be forward biased. The junction cannot be made forward biased till the voltage applied becomes greater than the cut-in voltage of the junction, which is generally 0.7 for silicon and 0.2 for germanium transistors. So in that case, this goes positive above this particular cut-in voltage only. So the signal is produced with a shift here. So this much portion is missing from the actual output signal. So the output current signal will have a missing portion like this, where the output is 0. That is this duration is determined by the cut-in voltage of the transistor. So this is giving rise to a distortion in the output waveform of the class B push-pull power amplifier, which is known as crossover distortion. So here the nature of the output signal gets distorted and no longer remains same as that of input. So this is because of the cut-in voltage of the transistor. So with this, I am ending the discussion on class B power amplifier and distortion in amplifiers. Thank you.